So today we're going to take the Pythagorean theorem and apply it to real-world problems. We're also going to turn our thinking, that's where we're going to start, and talk about something called the converse of the Pythagorean theorem. That's, like I said, where we're going to start, and we're going to head into our book to page 413 to kind of take a look at this. So remember that the Pythagorean theorem says that given that you have a right triangle, so I hand you a right triangle, you know that if you take the two legs and raise them to the second power, add those together, it'll equal that third longest side called the hypotenuse squared. A squared plus b squared equals c squared. Today we're going to turn it around, and I'm going to hand you a triangle, but I'm not going to tell you what kind of triangle it is. And you're going to use the Pythagorean theorem. You're going to kind of jam the three sides of your triangle into the Pythagorean theorem. And if the Pythagorean theorem works, if you get the left-hand side of the equation equaling the right-hand side, then it is a right triangle. We're going to go one step further, and if it doesn't equal, we're going to try to figure out what kind of triangle it is. So there's three possibilities we're going to talk about. Is it a right triangle with a 190-degree angle? Is it a obtuse triangle with an angle larger than 90, less than 180? And finally, is it an acute triangle where all the angles are less than 90? So we're going to take it a little bit further than the book. So converse, again, means sort of opposite, coming at it backwards. So today you're going to notice that I'm going to hand you a triangle, and it has one side 5 inches, one 12 inches, and one 13 inches. You can imagine that I hand you 3 straws those lengths, and you're going to put them together in a triangle. Will it be a right triangle? So the first thing that you're going to do is you're going to ask yourself which of the 3 sides would be the hypotenuse if it's a right triangle. And remember that the longest side would be the hypotenuse, so he would be the C. And you'll notice they're going to put a little question mark here because we don't know if this is going to work yet. So the 2 legs would be 5 and 12, so I put the 5 in for one of the legs and square it. I put the 12 in for the other leg and square it. And then does it equal the longest side, what would be the hypotenuse squared? And now I start doing the math. 5 to the second power is 25. 12 to the second power is 144. And this time I do have a number over here, so 13 squared equals 169. And I'm still questioning, am I going to get the same number on both sides? And when I add 25 plus 144, I do. So since the Pythagorean theorem worked on this triangle, the triangle I have is a right triangle. So now let's try 2 more. I'm going to ask you to pause the video. I want you to write these 3 numbers into Pythagorean theorem. So don't forget, they're going to look for the largest one first, and he would be what would be your C. So you're going to write an a squared plus b squared equals c squared using these 3 numbers. But right now the equals is a question mark. You're going to solve it down. If you get the a squared plus b squared to be the same number as the c squared, it's a right triangle. Otherwise, we're going to talk about what kind of triangle would it be. That's where we're heading next. But see if this one is a yay or a nay. So pause the video and try this one. Okay, so let's see how you did. The hypotenuse, if this is a right triangle, would be the 60. So he's going to be your C. So I found out that this guy is a right triangle because I put the 36 squared plus the 48 squared equaling the longest side squared, and I'm hoping this is going to work. 36 squared is 1,296, 48 squared is 2,304, and 60 squared is 3,600. And when I add these 2 numbers together, I get the same value. Okay? So now what I want you to do is pause the video and see what happens with this one. And if it's not right, we need to talk about what's the next step to discover what kind of triangle it is. Okay, so the 7 would have been the hypotenuse this time. So I'm going to put him as the c squared. Don't just go left to right. The longest would be the hypotenuse. I'm going to square the 4, square the 5, square the 7, and 16 plus 25 does not equal 49. This is not a right triangle. So my question is, what kind of triangle is it? So if you notice, the would-be hypotenuse is bigger He's too big. Look at the hypotenuse, c squared. This is what the hypotenuse would have been if it was a right triangle. Because he is too big, you're going to have to stretch open the triangle to accommodate this really too big third side. So this would be actually an obtuse triangle. So when the hypotenuse, or what should be the hypotenuse, is too big for the triangle, you have to pull open the angle, which means it's going to be an obtuse. So basically, here's kind of what happens. So let's start in the middle with the green. If it works out that a squared plus b squared equals c squared, like we just saw a second ago, that would be a right triangle. The converse of the Pythagorean theorem shows us it works. Now, if you get, like we just did, a hypotenuse that is too big, you need to stretch out this angle beyond 90 degrees to accommodate that third side that's too long. Always look at it from the c squared perspective, okay? Now, let's just say that it had been too small. What if we did the Pythagorean theorem with the three sides, and we found that the a squared plus b squared is bigger? In other words, that third side is too small for the right angle. This time we have to squish the angle in, which means it would be acute. So Goldilocks and the three squares. If c squared is too small, the triangle is acute. If c squared is too big, the triangle is obtuse. And if c squared is equal, the triangle is just right. And that's called the converse of the Pythagorean theorem. We can use the Pythagorean theorem to prove what kind of triangle we have. So on page 423, you can see what type of triangle is formed. So we've got these three sides. So this would be the hypotenuse if it's a right triangle. So there's my start of my work. I'm going to square the 21, the 72, and the 75. I'm going to add the 441 and the 5,184. And look, it is a right triangle because it is just right. So it is a right triangle. Let's talk about now some cases of where can we see the Pythagorean theorem in the real world. And I just showed you one here that we can talk about sort of a parasailer. But we're going to move on to another example, which is the infamous ladder leaning on the building. And I say that jokingly because this is just such a typical Pythagorean theorem problem. Although I think this one is a little bit backwards, but let's solve it. Write an equation that can be used to find the length of the ladder and then solve it round to the nearest tenth. My feeling is that you would know how long your ladder is, so that's why I say this problem is a little backwards in terms of real world, but we're going to take it because it's what we got. So basically, notice that the distance from the building and the building itself and the ladder form a right triangle. So as long as this building is truly vertical and not leaning, you've got a right angle in this corner. So notice that the foot of the ladder is 8.75 feet from the base. And if you go up the side of the building, the ladder reaches 18 feet. Now your ladder has to be longer than 18 feet to reach up 18 feet. Otherwise it'd be right against the building. So this again is the longest side. This would be your hypotenuse. So we're going to take a squared plus b squared equals c squared. We're going to square both our legs, add them together, and not forget that your ladder is not 400 feet long. You've got to take the square root. The negative is kind of stupid because it's a ladder. You can't have a negative length ladder. So if you take the square root of that 400.5625, it rounds to about 20 feet long. So the important thing to remember here is that you're still doing the same steps, the substitute, in this case, add, the substitute, the square, the add, take the square root, but you're going to remember to put your units in at the end. Here's another problem. This time, if you look at this triangle between the two planes that are flying, you can see that the right angle is in the lower left here. And this time we're missing one of the legs. We've been given the hypotenuse, which is the diagonal distance, 12 miles between them. We've been given the horizontal distance, which is 10 miles, and we're looking for the vertical distance. So this time it's going to be the backward sort of problem here. So, and we're going to round to the tenth. So we need to find the height of that plane, the difference of the height between the two of them, really. So notice I'm crossing this out in the book because we've always looked at it, if we're given the hypotenuse, it's going to lead the way in a subtraction, right? So there's the hypotenuse squared minus the leg squared equals the other leg. I square it, still equaling that missing leg squared. I subtract it, still equaling that missing leg squared, and finally I take the square root and I round it to one decimal place, which is a tenth, and it will be about 6.6 miles. So here's another example where the Pythagorean theorem can be used. Now, we often don't think about it, but we look at a ramp and we see the right triangle, but there's actually a ramp hiding in a staircase. So let's say that Mr. Parsons wants to build a new banister, like that would be a kind of a new, almost like a handrail kind of thing. If the rise of the stairs of the building is 5 feet rise, that's your vertical distance right here, and the run is 12 feet, so I think you're kind of running along the ground here. So what would the length of the new banister be, which he's putting in here? So it's not really a handrail. It's going to be the bottom of putting like the spokes up, if you think about it that way. So I'm going to ask you to pause the video, write your equation, and solve it. Let's see how you do in a minute. Okay, so the first question is, which version of the Pythagorean theorem are we going to use? We're missing the hypotenuse, so you should be adding. So 12 squared plus 5 squared equals c squared. I squared the 12 and 5, still equals the hypotenuse squared. I'm going to add it as my next step. And finally, I'm going to take the square root. Works out to be a perfect square there, so we get an exact answer, which is 13 feet. So yeah, inside of a staircase is a right triangle that oftentimes architects and builders have to think about what's going on there, and they use the Pythagorean theorem. Okay, so we just have 2 more examples here. Let's say we have a 12-foot flagpole. These are always the types of Pythagorean problems. It might be a flagpole, it might be a tree, it might be a cell phone tower, something like that. It's placed in the center of a square area. To stabilize the pole, they're going to put a wire that's going to stretch from the top of the pole to each corner of the square. The flagpole is 7 feet from each corner, so it runs along the ground. That's 7 feet. And we also know that the flagpole is 12 feet, and they want to know what's the length of these wires that they're going to put around the flagpole. So if we notice right off the bat, here's our right angle, right? Would be hopefully the flagpole is straight up and down with the ground, making a right angle. So we've got the 2 legs. So we square one leg plus square the other. It's got to equal the missing wire squared. So we substitute, we square, we add, we take the square root. In this case, you're going to have to round because 193 is not on the perfect square trail. It comes out to be about 13.9. Don't forget your units. You're going to need wire. That would be at least 13.9 feet. And finally, another place that you can find right triangles inside of a cone. So if you look, I've kind of traced. I'm not sure if your book has all these lines the way I've done them here, but I made it very obvious for you. So this is the top part of a circus tent, and it's in the shape of a cone. So you kind of have a cone sitting on top of a cylinder. More on that in the spring, by the way. It has a radius. A radius is the distance from the center of the circle to a point on the circle. So it's like half the way across. So that's 50 feet. And the distance from the top of the tent to the edge is 61 feet. How tall is the top part of the tent? So they want to know, what is this height? So here again, we're going to use our Pythagorean theorem. We're going to round to the nearest whole number this time. How about if you pause the video and see how you do with this final example? Well, I'm just going to show you a smaller kind of just pulled off that triangle in case you're having trouble seeing it. This is kind of what we're looking at. We were given the hypotenuse. We've got the longest side, so you shouldn't be adding, right? So we're going to put him as the leader in a subtraction. Don't forget, you square the hypotenuse minus the leg squared will equal that other side. Yeah, it can be h, it can be b, okay? It's an unknown right now. Square the 61, square the 50, write that down. We're going to subtract, because if we add, we're going to get a number bigger than 61, and this side can't be bigger than 61, so we should be subtracting. And then I'm going to take the square root, and it's about 35 feet. Remember, this time they asked for the whole number. You've always got to read your rounding directions there. They didn't want the tenth. So final answer, 35 feet. So today there were two ideas. One was called the converse. That is, hey, here's a triangle. Is it a right triangle? And you jam those three sides into Pythagorean theorem in all three places. I gave you all three sides, putting the longest in the c squared spot. You do the math. If you get an equal statement, the legs add up, the squares of the legs add up to the square of what would be the hypotenuse, it's a right triangle. If the hypotenuse side is too big, you got to stretch out that angle so it's obtuse. And if the hypotenuse side squared is too small, you got to smush it down to make it an acute. Well, another thing we did was take the same ideas we've been doing with the Pythagorean theorem and just see some real-world applications. So now it's time for you to practice. So next time I see you, we'll be doing some practice. Have a great day, everybody.